And we are going. Okay. So what we're going to do today is we're going to review what we talked about on Wednesday, and then we might finish up a chapter today. If not, we're going to go probably at least to radioactive half-life on page 38. So what we talked about on Wednesday was, again, we talked about the atomic structure and where each of the charges or each of the subatomic particles that we're interested in live. And again, we're only going to focus on the three. We're only going to focus on proton, neutron, and electron because they're the only ones that really matter to us. The proton and the neutron give mass to the nucleus, and especially of those two, the protons. And the electron is what we use in characteristic X-ray creation. So the quarks and all the other subatomic particles really don't matter to us. Just the protons and the electrons, and then the neutrons. We'll talk about their significance here in a bit. So we talked about where they live. The protons and the electrons live inside the nucleus, and the electron exists in the shells outside of the nucleus. We talked about the positive and negative charges, or the charges of each. And the proton has what kind of charge? Positive charge. The electron has a negative charge, and the neutron has a neutral charge, but we say it's neutral charge because it has both, right? It's not neutral because it lacks charge, it's neutral because it has both. Now, I promise we're going to get to that today. So then we talked about the electron shells and the numbering of the shells. Lettering of the shells starts with K shell being the innermost shell, and then it goes alphabetical from that. So it's K shell is the innermost shell, K shell, L, M, N, and so on. So we talked about the electron shell capacity, right? And we had two things that we talked about in electron shell capacity. One was that you could calculate how many electrons maximum any shell could hold with what formula? 2n squared, right. So 2 times the number, K being 1, 2 times the number, and that number squared. So it would be 1 squared times 2, or 2 squared times 2, or 3 squared times 2. And you can figure out exactly how many electrons each shell could hold. And I talked pretty extensively about the fact that you could fill up shells, or you could extend 2 shells before filling up specific shells. And you could do some searches online to find that. But we'll talk a little bit about that today as well. All right, so those 2n squared was the electron shell capacity. We said that the outer shell was never going to have more than 8, regardless of what the 2n squared gave us. The outer shell was never going to have more than 8. And we also said, and Bouchon didn't really touch on this, but we also said that the outer shell wants to have 8. The most stable condition that we can be in is to not only be electrically neutral, which means that we have the same number of positive charges as negative charges, same number of protons and electrons, but also to have 8 in the outer shell. Again, we're going to talk about that here in a bit. And we talked about what keeps them in the shell, and we've got 2 different forces. We've got centripetal force and we've got centrifugal force. And in our solar system analogy, the centripetal force would kind of be like gravitational pull, right? It keeps it in orbit, keeps it from flying out into space. And the centrifugal force is basically the speed with which the electron travels that keeps it from falling into the nucleus. So you had to have a balance between those two. So we talked about electron binding energy, and there were 2 specific things, really 3 specific things about electron binding energy. One is that it's specific to, in any shell, it's going to be specific to the type of atom that we're talking about, right? That's why we get characteristic radiation and the specific energy level that we do. But it's always greatest where? In the atom itself. Which electrons are most tightly bound?
The K shell.
What's that?
Toward the nucleus.
Closer to the nucleus. K shell is the tightest bound. and then L shell, and so forth. So the closest to the nucleus, the closer they get to the nucleus, the more tightly bound they are. Okay, so what's the other thing? What type of atoms have the most tightly bound electrons? Hydrogen, tungsten. Okay, what's different about tungsten than hydrogen?
High atomic weight.
A high atomic number specifically. So the higher the atomic number, really, the more tightly they're going to be bound. So what does atomic number give us? And atomic weight, really. It's a
Density.
big fat nucleus, right? So if we have electrons that are close to the big fat nucleus, we got a lot of binding energy there. So greatest in elements with a large nucleus, and that would be a lot of positive charges, a lot of protons. And the closer to the nucleus we get, the more binding energy we see. Okay, everybody okay with all that? Okay, so we're going to get a little bit deeper into atomic nomenclature. Good, it works. Somebody brought this on. So we talked about atomic mass number. What was atomic mass? What was the measure of atomic mass of a subatomic particle? We had atomic mass unit and we had atomic mass number. What were the difference between those two?
One is, I'm probably wrong. One is just the proton count, right?
No, not just the proton. So we got a chart, and it's on page 30. So the atomic mass unit is the actual mass of the subatomic particle, right? And again, the largest subatomic particle that we're going to focus on is the neutron. Slightly less large than that was the proton, and then the electron was very, very small. So the atomic mass unit is the actual mass, as opposed to the atomic mass number would just be the rounded off version of that. So taking things a little bit deeper, all of those go into the elemental mass. But really, the atomic mass, or the atomic mass number of proton and neutron is most of that, because most of the mass of an atom is found where? In the nucleus, right. Most of the space in an atom is empty. It's empty. It's just empty space, just like the solar system, right. So if you flip over page 30, you see atomic, no, that's not where I want to be. Atomic nomenclature on 34, it starts talking about atomic nomenclature and different types of atoms. So you got 4 different types of atoms. You got isotope, isobar, isotone, and isomers, or the nomenclature that we're going to talk about to start with. We're going to talk about all of those just a little bit. We'll talk about the difference between them, and we're going to talk about the ones that we're most interested in and that we're going to talk about in depth today. So you have isotopes. So fundamentally what we're talking about here is the nucleus, okay? Just the electrons are just kind of out there and they're doing their thing, but we want to focus on the nucleus here. So with the nucleus, we've got the positive charges and we've got the neutral charges, which are neutral by virtue of having both charges, right? We'll go ahead and say that we've got electrons out there as well. And we'll say, what's the difference between these things? Right? What specific is there about these things that are different? Why do we have 4 different names for them? So what does it say about isotopes?
Same number of protons.
Same number of protons. Same number of protons. So we have the same number of protons, and then it's got what?
Different number of neutrons.
Different number of neutrons. Right. So, regardless of what the number of protons we have, protons being positive charges, I'm beating this to death, the positive and negative charges, because when we take the test next week, I don't know why, every year we have people flipping these around and not getting that protons should equal electrons, and if they don't, what do we have?
No,
What?
an ion.
An ion, exactly. Is an ion a neutral state that the atom wants to be in? No, it's not. Okay, so we've got the protons. Regardless of the number of protons, what should they equal? The number of
Electrons.
equal the number of positive charges, which are the protons, right? So if we have the same number of protons, different number of neutrons, what's the difference between the two? Hmm? The mass. The mass is different, right? So elemental mass is different. But fundamentally, what do we have if we have two different isotopes? It's an isotope of the same, what's the word missing there? Same number of protons. Number of protons determines the element, right? Atomic number in your elemental table is just the number of positive charges. Okay, so let's flip back to page 29. All right, so you got the elemental table there. So that number right above the chemical symbol is just the letter that represents the atom. The number right above that is the atomic number. The atomic number identifies the number of protons. The number of protons identifies the element. So all the same thing, right? So atomic number is the same with different isotopes. So what do we have? We got different mass, but we got the same atomic number, so we have the same element, right? So the same element chemically behave just a little bit different, sometimes radically different. We'll talk about that in a minute. So the next one I think was isobar, right?
Yes.
So what does isobar say?
They're the same atomic mass.
It has the same atomic mass. Difference, the mass is same. So maybe I should have just gone with this. Mass, same. No, this was different. So mass here was the same. This mass was the same, but what about protons?
They're different.
Different, right. Different. So what can you tell me about isobars? You got two elements that have exactly the same mass, but they have a different atomic number. What do you have to have there? If you got a different atomic number identifies number of positive charges, number of positive charges identifies what?
The element.
Element, right. So if you have two isobars that have the same mass, then you're gonna have a varying number of neutrons to protons to come out to that same mass, right? So, I don't know, yeah. It's gotta be different, but different from what? You know, I mean, if you have, one element that's got atomic number of 50 and atomic mass of 60, and then you got another one that's got atomic mass of 60, but it's got an atomic mass of 40, and you got another one that's got an atomic mass of 50, but it's got an atomic number of 50, then you got a lot of different possible combinations there, right? So isobars are really, of all of these, or both of these that I've talked about so far, almost insignificant. But we have a set number of protons in each type of isobar, which means we have, if it's chemically or electrically neutral, what do we have? Equal number as what we have in protons, right? Positive charges identify the element because that is our atomic number. Negative charges should equal positive charges, should, unless we have an ion. Okay, so what's the next step? Acetone? Acetone, that's right, because the last one is isomer. Okay, so what does acetone say?
Same number of neutrons,
Same number of neutrons.
a different number of protons.
So, based on that, what do you know? You've got that. Different number of protons, different number of positive charges. Positive charges identify the element, right? So what do we have? With two different isotopes. Two different things, right? Two different things. But if we have any combination of those and we've got a set number of protons, what should we have?
So
The number of electrons, right? So the protons and electrons should match up. So our elemental mass, it doesn't even tell us, right? It doesn't even say anything about the mass. So these things are different all the way across. Now, between these three, both of those are pretty insignificant with the exception of knowing, atomic number, positive charges, and the positive charges should equal the negative charges and all that. So the last one, what does it say? Same atomic number. So two isomers, what can you tell me about two isomers? Same thing, right? So what about neutrons in isomer? What does it say?
same protons and neutrons.
Same number of neutrons. So what can you tell me about electrons? It's either an ion or the number of negative charges equal the number of positive charges, right? So what are two isomers? Basically twins, right? So we're going to talk about, pure substance is what an isomer is, identical elements. We're going to talk about isotopes a little bit later today, isotopes, where we have an unstable reaction or unstable atom is when we have an atom, not all isotopes are unstable. Okay, so we have isotopes that have different number of neutrons that are perfectly stable and they really kind of behave in the same ways. But you've heard of radioactivity, right? Radioactive meltdowns, nuclear bombs, things like that. Unstable radioactivity, and we've talked a little bit about it. Radon, things like that. What differentiates an isotope from an unstable isotope is really the number of neutrons. If the elemental mass gets too heavy, to support itself, then it's going to undergo a reaction that seeks to try to get rid of some of that weight. Okay, so if we have 15 elements of oxygen, let's say, in different presentations, different elemental masses, what's the difference between them? They're all oxygen, so they all have the same protons. So what's got to be different?
The neutrons.
The neutrons, right. So the neutrons are going to be different in that case, and in some cases it's going to be too heavy to support itself. It's got to get rid of some neutrons. So we'll talk about that in just a minute, but I think we've got to get to something else beforehand. Yeah. So hang on to that. I'm going to leave isotope up there. I'm going to erase everything else because for the rest of the discussion today, they don't matter. All right, so what we have are elements. Elements are differentiated from each other on the elemental table by atomic number, which is number of positive charges. But in nature, we just don't often see pure elements, right? And the air you breathe, yeah, it's got oxygen in it, but it's also got hydrogen, nitrogen, all kinds of other things. So separating those things out all by themselves is pretty rare. The most common thing that you interact with inside of your body anyway is water. Is water an element? No, it's not. It's made of elements. Specifically, it's made of two types of elements in a combination with, three individual elements, and that is H2O, right? So what we have is two hydrogen atoms and one oxygen atom that joined together to create a molecule. Okay, so in this case, we got three different elements joined together to create a molecule. So that is a molecule. This is where the Dalton atom comes in, and its combination, or its contribution to the atomic model was the joining with the hooks and eyes, right? They don't really join with hooks and eyes, but that was his analogy. So H2O creates a molecule, you get a combination of a molecule together and you create a compound. So a cup of water, your water bottles, it's a compound of water, right? It's not pure water, and we'll talk about that later in the semester in the properties of pure water. So we've got a molecule, group of molecules creates a compound, but how do we make those join together? Well, there's two different ways. One is ionic, and I'm going to take these out of order from what you see in the textbook, because ionic bonding is the easiest to explain, because you know what an ion is, right? An ion, the definition of an ion is just that it is a element that has a charge. That's all it means. It's a charged particle. So the most common ion, or one of the most common ions, and certainly again one that you're familiar with, is table salt, right? So you got table salt, sodium chloride, no, that'd be too easy. Sodium chloride. So in sodium, we talked about electron arrangement on Wednesday, and again we've got the nucleus, and then we've got the electrons. We said that the electrons furthest from the nucleus are the most weakly bound, right? Well, sodium atom has a valence electron all the way out in its outermost shell that's loosely bound. And again, we're going to talk about creation of electricity and flow of electricity later on. We'll talk more about the electrons, those loosely bound electrons. But it's loosely bound, and it's only got one. And the chloride also has loosely bound electrons in its outermost shell, but what it's got is a space for an extra electron. So what happens is that because it's got basically a hole, almost a vacancy, it hangs up a no vacancy, or a vacancy sign rather. And what happens is it strips the electron from the sodium. Now it's an ion, and it comes over and joins with chloride. Okay? So if we were sitting on two different elements and they were both neutral, so our positive equals our negative, positive equals negative, and if one of these negative charges skips out on the sodium and it joins up with the chloride, what happened to my sodium ion? Or, I just gave it away, sodium atom. It loses the negative charge, and therefore it becomes positive. Now it's positive, right? It has one more positive charge than negative charges, and that makes it positive, right? So now it is what? It's an ion. It's a positive ion. The chlorine atom was neutral, so we had those two equaling, right? So now that's positive. It was neutral, and now it gained an electron, so it's an extra negative charge, so our overall charge of the atom is now negative, right? So what is it? It's an ion, right? So we got two ions. One is negative, one is positive. Opposites do what? attract, right. So now, what's gonna happen is even though it gave it up, it's gonna kind of want it back to a degree, and it shares the electrons so that now they're both, again, neutral, but they're joined together, okay? So neither one of them's an ion. They both have a neutral charge. It's just that they're sharing electrons. Okay, so that's table salt. Ionic bonds, that is an ionic bond. Ionic bonds share electrons. Actually, both types of bonding share electrons. It's just how they do it. So ionic bonds share electrons, and the purpose for sharing the electrons is to maintain that neutral status. That's the whole reason. That's the only reason that they're doing it, is to maintain the neutral status. So they're easy to create, easy to break up. They join together fairly easy. They can be torn apart really easily as well. So you're good with ionic bonding. Because the next one gets a little more complicated. The other is what we call covalent bonding. All right, so skipping back. How many electrons can any shell have?
8.
Any shell can have
2.
2n squared, right? How many electrons can the outer shell have no more than?
8.
8. How many electrons does the outer shell seek to have?
8.
8, right. Now looking back at your elemental table, what is the atomic number of hydrogen? 1. So if you add 7 more electrons to hydrogen, what do you have? You ever gonna add 7 more electrons to hydrogen? No. Why? Because it would what? It'd be an ion. It'd be a very strong ion. There'd be a lot of negative charges. Well, I have 1 positive charge. How are you gonna have 8 negative charges? I have no clue. You know, it's an honest question. I don't know. You can't do it. Right? But how many does it want to have? 8. Right. Okay, so now look at oxygen. What is the atomic number of oxygen? 8. Right, so how many is the inner shell going to have? 2. Right, the outer shell is going to have 6. Right, because our positive charges and negative charges should be equal, so you got 2 in the inner shell, so 2 plus 6 is 8. Right. How many does it want to have? 8 in the outer shell. If you added 2 more to the outer shell, what would you have? An ion. Okay, is it going to maintain that ionic status? It's going to seek to get rid of those 2. But if you took oxygen, okay, so that's an O, that's not a nucleus, that's an O. So you got the nucleus here, let's just get rid of that. We'll say positive and neutral. Okay, so in the innermost shell, you're gonna have 2, right? So in the next shell, what you're gonna have is 1, 2, 3, 4, 5, 6, right? We're all good with that. It wants 8, it's got 6. You know, it wants 8 in the outer shell. It's got 8 electrons because it's got 8 protons, but it wants 8 in the outer shell, right? Now along comes hydrogen. Hydrogen has how many in the outer shell? It only has 1 shell, right? So it's only got 1 hydrogen. So it's got 1 proton, which means it's got 1 electron. And if we have another hydrogen over here, it's got 1 proton, so it's got 1 electron. And if they can combine and share all of the electrons, and all of these rotate around this nucleus, then how many electrons effectively does this nucleus have? 8. And if they do this figure 8 type shape and then it goes all the way around this nucleus, how many does this one have in its outer shell? 8. And then it goes around, does another figure 8 around that one. How many does this one have in its outer shell? 8. Okay, so the purpose for, the attempt at covalent bonding, what it's trying to achieve is to get 8 in its outer shell, outermost shell. So sharing electrons just like the ionic bonding does, but it's sharing electrons for a totally different reason. With an ionic bond, it's just to neutralize the ions, to take that negative and positive charge and get rid of those, and to join up, share the electrons so that we don't have that negative and positive charge anymore. The purpose for covalent bonding is to get 8 in the outermost shell. Okay? So the difference in creation and destroying those bonds are totally different as well. Ionic bonds, easy. Covalent bonds generally take something nasty to make it happen. It's a violent interaction to create even water. You know, this is water, right? H2O, this is water. You ever see water being created?
Yeah.
When?
Well, I mean,
You're right, I just want to know.
when it's, I can't think of the name, like on the outside of the cup, when you have.
Condensation.
Condensation.
No, that's not creation. That's just, it's, have you ever flown? This is really kind of wild. I hadn't noticed this. I got a buddy that used to be a pilot, and it wasn't until he pointed it out. And I used to work on airplanes. You may not know it, but I was an aircraft mechanic in the Air Force. We used to turn on the auxiliary power units and you know, turn on the air conditioners in the system. Air conditioners suck moisture out of the air, which is your hint here where I'm going with this. Have you ever flown and gotten a cup of ice water? Next time you do, or if you ever do, just set it down. Don't drink it. Just set it down. You will not see condensation on that cup. It'll never happen because the air conditioner is so effective on an airplane. It's sucking all the moisture out of the air, including the moisture that would condense on the cup. So what you're actually getting there is just atmospheric moisture collecting on the cup. So no. Good try, good guess, but no. Anybody else? It's kind of wild, really. You've seen it probably your whole life. It's a shame you don't see, you know what, we're gonna pull this up, if I can make it happen.
I watched this movie, it was called Going to Mars or something.
Now you're getting there.
He combined oxygen and hydrogen together in gaseous form, and it seemed like condensation kind of built in on the plastic bag that he hung. And he drew.
Oh yeah, I know what you're talking about.
What's his name? Guy from,
Matt Damon.
yeah.
Yeah. I'm gonna show you exactly where you have seen water being made. Our technology will support it. I hate when I want to show something on the fly, especially when I'm a little bit excited about it, and then the technology is just draggy. I know that this particular video y'all probably haven't seen, might not have seen, because there has been no M in MTV in decades. But used to, oh, crying out loud. Used to, when MTV came on, it truly was music television. You know, it was just all day long music videos. And, you know, they had this little intro that came on. As close as you're ever gonna get me to sing. But what it showed was what you're just about, hopefully, just about to see. Intro. Okay. Okay, here we go. What do you see?
Nothing.
Hey, Miss Marley. A little better, right?
Yes.
Okay. Let me close this.
It looks like a rocket engine.
It's a rocket engine, space shuttle. Okay.
It's hydrogen they're burning.
Well, it's hydrogen and it's oxygen, and they're not burning it. What they're doing is they're venting it. So on an airplane and space shuttle, anything that has to create its own atmosphere, oxygen is kept inside of these little tubes or a little sphere in a liquid form. Okay, so they've got this stuff inside, like the airplane I used to work on, it had like 3 or 4 of these little spheres. It was a massive airplane I used to work on. And they were maybe the size of a basketball. There were 2 or 3 of these things. And it was liquid oxygen inside of it. And liquid oxygen, whenever it's condensed to the point that it's very, very cold, like almost 300 degrees below zero. Very, very cold. So that instead of having to carry these great big oxygen bottles, they can keep it in this little container, and they can expand it whenever it expands, like just a small amount of liquid oxygen will completely fill this room. Okay, so it pressurizes the airplane. Problem is that it's kind of like dry ice. You know, it's going to build up pressure, so you got to vent it. So that's what you're actually seeing here. So in a minute, what you're going to see is that the venting increases. All right, venting increases, and you're going to see down into the cloud that's being created here. And what you've got there are 2 different things. It's venting off both hydrogen and oxygen. So it's venting this stuff, and whenever the space shuttle gets ready to take off, or any kind of rocket that uses nitrogen and oxygen, gets ready to take off, the venting will increase.
Of the main engines as we prepare for ignition. T-minus 1 minute, 10 seconds, and counting. And just a couple seconds from now, we're just a few seconds away from switching to the redundant sense sequencer. It's 10, 9, 8, 7, 6.
Okay, you see what you see? Or do you see something change there, right?
Yeah.
You know what that was?
They started mixing the oxygen.
They started throwing sparks in between them, okay? So they start throwing sparks in between it, and then they increase the
5,
venting,
4, we've gone for main engine start.
and it ignites, okay? And that's what pushes the rocket or the space shuttle up. You know, and with the space shuttle, what you have is that primarily, but you've also got some solid rocket boosters, which is just rocket fuel. But that interaction, whenever they vented that off and then they threw those sparks, what you got was a controlled and sustained explosion. Okay? So when they hit the throttles and they increased that venting and actually, you know, were actively blowing the oxygen and the hydrogen out, then what they were actually creating was water, right? So that big cloud that you see with the space shuttle is partially smoke. That's a rocket right there. But that big cloud that you see with the space shuttle, part of it's smoke and part of it is just water vapor. Kind of wild, huh? Covalent bonding before your eyes, right there. So it takes a very violent reaction to create or destroy a covalent bond, whereas an ionic bond, it's very simple, really. I can tell y'all are massively impressed by that. I'm glad we took that little diversion. I thought it was cool. All right, so are y'all okay with the different types of bonding? Yes, okay. So radioactivity. All right, we're going back to different types of isotopes. So isotopes all have the same atomic number, which means they all have the same number of positive charges, protons, which means that for it to be neutral and not electric, not an ion, it has to have the same number of electrons, but they've got different number of protons. So what you have with different, again, with different isotopes are that the elemental mass can get so big and so massive and so heavy it can't sustain its own life, so to speak. All right, so what it seeks to do is to become something more stable. We've got two different ways to accomplish that. One is through what we call alpha emission, and one is through beta emission. Okay, so two different ways for a nucleus that is too heavy to support itself to become more stable. So what we have in something that is radioactive, an isotope that is radioactive, is what we call a radioisotope. Okay? So we've got radioisotopes that are both man-made and natural. And a radioisotope, again, just has too many neutrons. So it seeks to become stable. And again, we're going to look at these differently, one at a time. And with alpha particle, just like in bonding, alpha particle or alpha emission, alpha decay, radioactive decay is the process of trying to become neutral or more stable. And through alpha decay, what we have is emission of an alpha particle. Okay? So you got an atom, let's say, an atom, and we're just going to make up numbers here. Let's say we've got 20 protons. Okay? So we've got 20 protons, and we've got, let's say, number of neutrons is also 20, let's say. So alpha particle is actually a hydrogen nucleus. Okay? So what is nucleus? Protons and neutrons. Right. So what we get, let's say that this element with 20 protons, 20 neutrons is unstable and it's radioactive. So what it's going to do is it's going to emit an alpha particle. All right, so it's going to emit an alpha nucleus. It's going to emit an ion because it's just an alpha nucleus. It may pick up some electrons on the way out and just be a stable element of helium at that point. But what's the atomic number of helium? 2. Right. Helium atomic number is 2. So what it's going to do is it's going to take a chunk out, and it's going to be floating out here. It's going to actually take 2 protons and 2 neutrons with it. Okay? So it took that chunk out of the nucleus. It emitted from the nucleus of the atom. We got 2 protons, 2 neutrons. At that point, this is a helium nucleus, and it is also an ion unless it snags a couple of electrons on its way out, and then it truly is a helium atom. Okay? But what happened over here? It went down, both went down to 18. Right. So it went down to 18 protons and 18 neutrons. So through alpha emission, we eject a hydrogen, or a helium nucleus. What happens to our atomic number? They go up, or do they go down? Went down, right. So our atomic number through alpha decay, alpha emission, is atomic number decreases. Well, why do we say atomic number decreases? Well, because we lost positive charges. What are positive charges? They're protons. What does a proton determine?
The element.
What the element is, right. So if we flip back over to page 29, what is, calcium is 20, right? So what is it now? Is that argon, is that what A is? I don't know, yeah. So now we've created something totally different. It's a completely different element, okay? So that's alpha. And again, that's a very violent reaction, that's a very violent cause or a very violent means of decay, radioactive decay. The other is beta emission. And a beta emission is also totally different. So we've got this same thing, so we've got one positive, 18 positive and 18 neutral subatomic particles in the nucleus. Let's say it's still unstable, and it doesn't want to undergo another alpha emission. It can undergo a beta emission. And with a beta emission, what you get is an ejection of an electron. Well, where'd the electron come from if we've got positive charges and neutral charges?
From the hydrogen.
Well, we're still working on this argon nucleus right now. So how did we get an electron out of a nucleus where there was no negative charge? See, this is why I drop hints. This is why I drop hints. What is the neutron? Both positive and negative, right? So it kicks out a portion of one neutron. So is that neutron still a neutron?
No.
No. So now how many neutrons do we have? 17. But what did that neutron become by virtue of losing the electron? Proton. So now what happened to our atomic number? It went up, right? So atomic number increases with beta emission. So we get a high-speed electron coming out of the nucleus of the atom. Atomic number increases. The neutron is converted to a proton because it loses the electron, and atomic number increases. With alpha, we lose atomic number and we lose some elemental mass. With beta, we lose just a little bit of elemental mass because the electron almost doesn't have any, but the atomic number increases, okay? In both cases, they become something totally different, right? It's just a matter of how it became something totally different. Like, for example, you'd have to look this up. Plutonium or uranium, I think it's plutonium, eventually decays into lead. So it becomes something totally different. Okay? So y'all good with that? Any questions on that?
Is alpha emission, is it always gonna be 2 protons?
Yeah, it's always going to do a helium nucleus. So where we see both of these, and mainly the beta emission, but I understand I've done a little bit of reading on alpha emitters in nuclear medicine, but that's where we use radioactive decay. Nuclear medicine, it shows us physiology. It really doesn't show us anatomy very well. Anybody seen the nuke med scan? Real fuzzy, speckly looking, horrible for anatomy, excellent for physiology. And what we do in nuclear medicine is we inject the patient with man-made radioactive isotopes. We put them inside of the patient, and then we measure the response. So we put them to an element that's attracted to a specific, like if we want to see bones, we'd attach it maybe to calcium, send it to the bones. If we were looking at the thyroid, maybe some iodine. okay? So we put the radioactive material into it, and then we read how much radioactive material is coming off of it. So if you have an abnormal amount of radioactivity coming off of your thyroid, it indicates you've got hyperthyroidism. If it's too low, then it's hypothyroidism. So that's what we're measuring in nuclear medicine. It's imaging, but it's really imaging of physiology much more so than what it is anatomy. Okay? So, radioactivity. Radioactive half-life. Radioactive half-life is the measurement of how often this is happening. Okay? So radioactive half-life is predictable for individual elements. The reason we use man-made elements in nuclear medicine is because they have an extremely short radioactive half-life. You inject somebody with a man-made isotope and it's gone by the next day. You inject somebody with a natural isotope and it may take 100,000 years for it to go away. Okay? So, I like to use the example, and I think Bushon mentions it, carbon-14. Carbon-14 is one of the ways in which we radiometric date fossils. They're not really fossils, but things that are dead. Once it's fossilized, you're not really getting any kind of radiation off of it. But let's say we want to know how long ago the woolly mammoth died or whatever. It's not fossilized. You know, they found one like in a deep lake in Russia where the water temperature is so deep, the water temperature was really, really cold, so that it preserved the specimen so that they could actually radiometric date it. So what they do is they calculate how much carbon-14 is inside of that fossil or that specimen. Carbon-14 is a naturally occurring radioisotope you've got in your body, and you've got an amount of carbon-14 inside of you right now that if you were to die, we would know exactly how much carbon-14 you should have inside of you. But it decays at a constant rate, and it's somewhere around 5,100, I think it's like 5,184, but we're just gonna make it simple, and we're gonna say about every 5,000 years, it decays to half of its current amount. So around 5,000 years from now, you're gonna have half the amount of carbon-14 you have in you at the moment that you die, okay? That's a half-life, all right? Half-life, radioactive half-life, is the amount of time that it takes for a radioactive material to decay to half of its original intensity. So carbon-14. So if you die and you've got 100, I don't know, curies of carbon-14 inside of your body, and again, it's just for simplicity, then 5,000 years from now, that's a half-life. What you should have is half of that, which is 50, okay? So let's say this represents the entirety of the carbon-14 that you have in your body. In 5,000 years, that's how much you're gonna have. Right there. Okay, half-life. How much time does it take for an isotope of you know, in this case, carbon-14, to deteriorate to half of its original intensity? So that's a half-life. So now another 5,000 years, at 10,000 years, how much should you have?
1/4 of that number,
1/4 of what number?
the 5,000.
Well, the 5,000 is the time.
Oh,
So this was our original intensity, so it was one, after 5,000 years, we got to 50. So at 10,000 years, we're gonna have half of that, 25, right? So what you're gonna have a tendency to do is think, well, you know, it's 2 half-lives, so, you know, 5,000 divided by 2, or 100 divided by 2, you get, you know, but it's half of the half, okay? So in 15,000 years, we're gonna have half of that, which is gonna be 5, and then 12, and so forth, right? So it's half of the intensity you started with before the reset of the period of time. Now, again, the reason we use man-made is because the half-life is very, very short. If we used natural, then, you know, if they injected you with some sort of radioactive material, you gotta stay away from everybody for the rest of your life. Patient's gonna urinate, defecate, and break down, man-made radioisotopes very, very quickly, and it's gonna be gone out of the system, usually within a day. So, we don't really use this so much in diagnostic, but we use something that's similar to this in measuring our X-ray beam quality. And it's what we call half value layer. Okay? So half value layer is to diagnostic what half-life is to radioisotopes. So let's say we've got two X-ray beams. Okay? We've got two different X-ray rooms, so we've got X-ray tube in two separate rooms, and we make an exposure on both of them. Make an exposure in one, we set the same technique in both of them. Let's say our technique is, it doesn't really matter, we're just gonna say 70 kVp at 20 mass. And what we read off of that 20 mass, let's say, is 100 MR of exposure, okay? So over here, we've got 70 kVp, 20 mass, and that gives us 100 MR of exposure. In both rooms, everything is identical, right? So what we have in diagnostic, where we measure the quality of the X-ray beam, and we teach that the quality that the thing that you control quality with is KVP. The higher the KVP, the better the quality of the X-ray beam, right? And it's true. If you try to shoot an abdomen with 40 kVp, you're not gonna get anything. You try to shoot a finger with 40 kVp, you can get through it, right? So KVP is the quality, what you use to control the quality of the X-ray beam, but it's not the best measure. Because if you have two rooms that give you the same exposure off of the same technique, but one machine has greater levels of filtration, and what was the purpose for filtration?
Filter out like everything that's low energy.
Low energy X-ray photons, right, so you filter out the low energy X-ray photons. But if you've got two rooms that are shooting with the same MR per MAS output, and you put 1 millimeter of aluminum in the X-ray beam, so the X-ray beam's gotta go through that, 1 millimeter of aluminum. And let's say you energize this X-ray beam and you measure the MR before the aluminum and the MR after the aluminum. And after the aluminum, you've got 50 MR, then what can we say about that 1 millimeter of aluminum? It is this X-ray beams, or this room's half value layer, right? Because it cut the intensity by exactly 1/2. But let's say we shot with the same millimeter of aluminum in the other room, and what we're left down here with is 75 MR. What can we say about that? Did I get to half-life? No. So which one of these is a better quality beam? If quality is a measure of KVP and a KVP is a measure of penetration, which one of those two is a better quality X-ray beam? Did you choose A, or would you choose B? B. It'd be B. Because more penetrated through here than what did over here. Okay? So penetration, quality, KVP, but KVP is not the best measure because we had the same KVP. But we had more penetration over here, right? So a room with more half value layer, that is, let's say if we move this to here, if it took two half value layers or 2 millimeters of aluminum, so we got 1 plus 1 equals 2 millimeters of aluminum, then in order to cut it down to 50, then our half value layer here is 2 millimeters of aluminum, better quality X-ray beam, because it filtered out those low energy photons. Now what you're going to struggle with, again planting seeds, is quality of the X-ray beam does not mean quality of the X-ray image. Two totally different things. Okay, so what's KVP control? Quality of the X-ray beam, but on the image, have y'all gotten to that? If you increase your KVP, you shoot with low KVP, X-ray photons stop on the bones, right? You increase your KVP, it penetrates through the bones. So what it controls, again, is penetration. What that gives you is a longer grayscale. So our contrast is very high with low energy X-ray beam. Our contrast is very low with high energy X-ray beam. So the resulting image is going to be low contrast. Well, what do you want to see on an image? What does our contrast give us?
The density.
The difference in density, the ability to see the difference in density. We can't make a diagnosis if we don't have contrast, right? So X-ray beam quality and radiographic quality, image quality, are inversely proportional. So if this one's screwed up enough, I just, kind of complicated things for you. We're gonna get there eventually. That's not on this test, but we're gonna get there eventually. I want you to be thinking about that, is that X-ray beam quality and image quality are two totally different things. Okay? So finally, we get to different types of ionizing radiation. We're actually going to get to finish this. So we've got particulate radiation and we've got electromagnetic radiation. Electromagnetic radiation is where we're going to spend most of this semester. Particulate radiation are your alpha particles. Your beta particles are actually, even though they're tiny particles, they're still particles. Beta emission is still particulate radiation. And they can ionize. They can ionize very drastically. So what you're going to learn next semester is the quality, not of X-ray beams, but the quality of different types of radiation. And we ran through, a couple of weeks ago, the different measures of that we use in X-rays, the RAD, the RIM, the Rinkin, the Curie. And for diagnostic, with radiation and diagnostic range, 1 rad equals 1 RIM equals 1 Rinkin. Okay, so they're all the same. But 1 Curie equals 20 of each of those. So whenever you have a nuclear meltdown, is it the particulate radiation that's causing all the issues, or is it the electromagnetic radiation? It's the particles. Those big alpha particles are killing people quickly. The benefit, though, to the alpha particles is that they're big and they're slow moving and they stick to things. All right? And they don't tend to penetrate the way X-rays do. X-rays, the reason we get X-ray images is because they penetrate very, very well. Right? Alpha particles don't. When you see somebody going into a nuclear meltdown, what does the outfit that they're wearing look like? Looks kind of like a bee suit, doesn't it? You seen it? Yeah, that big white thing? It's actually made out of paper. The big bad alpha particles that'll kill you dead can't penetrate through paper, whereas X-rays go straight through it. So what we have, the beta particles go through it, probably, but the alpha particles won't. Okay? But the exposure to the alpha particles is what will absolutely destroy you. As opposed to electromagnetic radiation also is ionizing radiation. Understand, both of them are ionizing radiation. But not all electromagnetic radiation is ionizing radiation. The light from those fluorescent lights, do you suppose they're knocking around your electrons? Nah, not really. You get out in the sun, are you getting hit? You're getting to the upper register of electromagnetic radiation. And you're certainly getting cosmic rays, right? But also the infrared, the upper end of the visible spectrum probably are doing some ionizing. Certainly X-rays and gamma rays are as well. So X-rays and gamma rays are what we recognize as ionizing radiation. Ionizing radiation is just the type of radiation that is of high enough energy that it will eject an electron and therefore create an ion. And so in the electromagnetic spectrum, what we truly recognize as ionizing radiation is gamma rays and X-rays. And at one point, we could differentiate between the two we could still differentiate them by their origin, but we used to be able to differentiate them by their energy level. Gamma rays existed at a much higher energy level than X-rays. But we can create X-rays in the same energy level as gamma rays now. But gamma rays, how we differentiate between the two is gamma ray comes from the nucleus, okay? So we got a gamma ray that comes out of the nucleus of the atom, as opposed to X-rays, where do we create X-rays?
Electron.
We send electrons through the electron cloud, and we either create X-rays because it slows down, right? And that is a Brem's X-ray. Or it knocks out an orbital electron, creating an ion, and then we get a characteristic X-ray, right? So all of the X-ray creation occurs outside of the nucleus in the electron cloud. Regardless of whether or not it actually hits an electron, it's still in the cloud area, as opposed to a gamma ray comes out of the nucleus of the atom. That's the only thing that really differentiates the two. Okay? A lot of heavy stuff today. Any questions? No? All right, well, we're having a test next Friday. Wednesday, we'll pick up with chapter 3. We'll start on chapter 3, which some of this stuff we've already talked about. But we'll have a test on Friday over chapter 2. And if you didn't get the email, I set a calendar for testing. And I talked to Trina a little bit, and Trina's going to try to test on Wednesday, and I'm going to try to test on, or set the schedule to test on Friday. And so hopefully we'll be able to, for the most part, avoid Wednesday and Friday tests on the same day. But if you hadn't checked your email, check your email and see that schedule. All right? Y'all have a good weekend.